Hello everybody, this is Solar Tiger with another video, and as requested by a fellow YouTuber, this video is going to be about how to wire up your solar power system. So I'm going to show you how to wire up your solar power system. So let's begin. So at the beginning of your solar power system is obviously your solar panels, and they are the start of the system. So outside I have the solar panels on the top of the shed. There are the three 100-watt solar panels wired in series. This video is about using an MPPT charge controller. So the system I'm describing uses an MPPT solar charge controller. So that means that you wire your solar panels for a high voltage. So as I said, my solar panels are wired in series. I have three 12-volt solar panels wired in series. The solar panels actually output about 20 volts each, so 20 plus 20 plus 20 in my case equals approximately 60 volts. Although the fellow YouTuber I'm doing this video for has only two panels, so he will see approximately 40 volts. So the wires come from outside. That's the cable you can see here, and it comes out of my wall down there. And for the solar, it's the two terminals on the right. So that's all we're concerned about here. So from the solar panels, the wire goes down there, up, up and up. So in the diagram, here are the solar panels, goes up, up, up here, and then I will go back to my system. So if I go to the diagram, the solar panels go to a switch and a meter. Now it doesn't matter which order you put them in. Does meter come first or the switch can come first, that doesn't matter. So over here the solar comes up the red and black wire, the thinner ones, and I have my meter first. So this is a DC amp meter or ammeter, and this one has a scale of 10 amps. My solar panels can put out about 5.8 amps, about 6 amps maximum. So this meter will cover 6 amps with no problem. The YouTuber I'm doing this video for has two panels of approximately 100 odd watts, so he will see about 6 amps the same, but at about 40 volts maximum. So the plus of the meter faces towards the solar panels, as shown in this diagram. Plus of the meter points towards the solar panels. If you wire your meter backwards, the needle will try to go backwards on the scale, and that's bad for your meter and you can damage it. So from the meter we come to the switch. I'm using a circuit breaker here, but you can just use a switch. The whole point is just to switch off the solar panels, to disconnect them from the charge controller. So that's the switch here. Focus. I have a circuit breaker, but I'm using it just as a switch mainly. Now DC circuit breakers do have polarity, so the plus on the breaker would go towards the solar panels. I haven't marked that on the diagram, but the plus on your circuit breaker goes to the plus of the solar panels. If you're just using a normal switch, then you can wire it either way around, it does not matter. The reason you have a switch here is that when you first connect your solar charge controller to the battery, it needs to detect what voltage battery bank you're using, and it can't do that correctly if the solar panels are connected. All the manuals say that you connect the charge controller to the battery before you connect the solar panels, or you switch them on. That's why there's a switch there. So after the switch and the meter, the wire goes to the charge controller, to the solar input of the charge controller. So in this case, the minus of the meter goes to the plus of the solar input on your charge controller. So here I will show you that's the plus of the breaker. So the plus of the meter goes towards the solar panels, minus of the meter goes to the breaker or switch. If you're using a breaker, it would be the positive terminal. Then out of the breaker, the minus terminal goes to the plus terminal of the solar input on your charge controller. So minus of the breaker to the plus of the solar charge controller. That's this diagram, this point here on the diagram. I'm sorry about the shaky camera, it's because I'm having to hold it. So the charge controller has 3 sets of terminals: solar input, battery, and the load or output. So here is the charge controller, and we have input solar, battery, and load or output. I'll try and focus on it a bit. There we go. So if we go back to the diagram. Right, so we dealt with the solar input, we will deal with the battery. So on your charge controller there's a pair of terminals marked battery, or just might have a battery symbol on it. So the plus wire from the charge controller needs to go to a fuse. A fuse you can wire around either way round, and the breaker has to be wired around a particular way. Now in this case, the plus of the breaker must be wired towards the plus of the battery. That's the way it works in this case, because this fuse or breaker is here to protect the solar charge controller. If it goes wrong internally and it shorts the battery input together, as an example, the plus and the minus get shorted inside the charge controller, then your battery will try and push as much current as it could into the charge controller, which is very bad. This will get hot, smoke, and may even catch fire. And your wires might too, and the battery might overheat as well. So to prevent that, you need to use a fuse or a circuit breaker. The fuse or breaker that you use must match the charge controller. So if you have a 20 amp charge controller, for example, then you should use a 20 amp fuse or breaker. So that's how that works. Also, the fuse also protects the charge controller. If there's a short in one of your load devices, then it will blow the fuse or trip the breaker. Although most charge controllers do have protection built in, it's better not to rely on it, so better use a fuse or breaker. So from the fuse or the breaker we go to a switch. So the main switch. The main switch should be wired as close as possible to the battery or battery bank. I write battery bank here. You may have 1 battery, 2, 3, however many batteries you got. This is the battery bank. The main switch and the fuse and the breaker need to be as physically close as possible to the battery bank. So that's just a safety thing. I shall go and point you to what I have. So here is the charge controller. This is the breaker stroke switch for the battery bank. So I can disconnect the battery bank up here. I do have a main switch right next to the batteries as well. So as you can see here, the plus on the breaker is wired towards the battery bank, and the minus is wired towards the battery terminals on the charge controller. Now, an update to the video that you've seen before, I have now made this wire the same thickness all the way to the battery bank, which I hadn't shown in previous videos. This wire is thicker because it outputs the most current in the circuit, and I'll explain that later. But this connection here goes to the battery bank. The battery bank is inside this box, as you've seen before, and my main switch is here, about 2 or 3 inches from the positive of the battery bank. So if you have any electrical issue, you can cut off the battery bank by switching this off here. Safety thing this is. So that's here. So basically, if you have any sort of problem, anything goes wrong, goes short, overheats, starts smoking or whatever, you can quickly disconnect the battery bank here. Or if you want to work anywhere on the system, you'll need to disconnect the battery bank and the solar panels before working on the system. So that is the battery bank. The solar charge controller also has a pair of terminals marked load, this here, and that's where you connect your DC loads. So on my charge controller, that's this terminal here marked with the light bulb. That's the DC load output. It might be called load or output or whatever it says in your manual, but that's the output. Now, I have shown here that you can have a meter to measure the current drawn by your loads, and the positive of the meter must go to the positive of the load output on the charge controller. Then after the meter we have a switch. This switch, you can put these either way around. The switch is here to turn off the loads. Again, if you want to work on this portion of the circuit, you can just turn off the load switch and still charge your batteries. So that's what that does. So after the switch comes a fuse panel. Now you can either use fuses or circuit breakers. Circuit breakers will probably be more convenient, as you can just reset them if they trip out, whereas fuses you need to replace. The only thing I can say is that fuses are a lot cheaper than circuit breakers, so that will sway your opinion on what you do here. You can either use individual fuses in the leads to your devices, or you can use a fuse box. I will show you what I have. So this is my system. There's a load switch and a load breaker. If you have the switch and you have the fuses, you probably don't need this breaker, so you can discount this. Then we go from switch to a fuse panel. This is simply a cheap automotive fuse box that you can buy from a car part shop. It costs a few quid, and it uses cheap blade fuses, standard blade fuses, or you can use plug-in circuit breakers, the car fuse type breakers. These are a bit more expensive. The only thing about those is that it's hard to get any value under 5 amps, whereas you can get fuses in all different ratings. I have 1 amps, 2 amps and 3 amp fuses here. Fuses are available in a bigger range of amperages than the circuit breakers. Also, if you fit these circuit breakers, the lid will not fit on the fuse box, so that's something to bear in mind. But if this circuit breaker trips, the little button will pop out, and if I allow it to cool down for a few minutes, I can just push the button back in and we'd be back in business. Whereas the fuse blows, I have to go and get another one of the right value, which can cause issues and tempt people to use fuses of the ratings that they shouldn't use because they haven't got one of the right rating. So fuses are cheap, but circuit breakers are better because you just reset them. Like this breaker here, this is a 5 amp breaker, and it covers what I'm using here. If I had a overload down the line here, this would pop out, the switch would just click up and it will cut off the load. So once I found out what the problem is and fixed it, I can just flip the switch back down again and we're back in business. So that's what we got there. Also, the charge controller does have built-in protections. Most of them do. So if there's a short in the circuitry somewhere, it will isolate the output, and most of them will try reconnecting 2 or 3 times, and if the fault is still present, it will latch out, and the only way to make it turn on again is to reset the charge controller. But it's better not to rely on those protections. It's better to use fuses and circuit breakers. So that's this part of the system. So fuses go in all the positive lines towards the battery, so the battery is in this direction, pointing this way. So you put fuses in all the positive wires. Now, if you use a separate fuse for each load, if one load goes faulty, all your others will carry on working. Whereas if you wire everything to one breaker, say I had did not have a fuse board here, and everything here was wired to this breaker, and this is a 5 amp breaker, so if something on this side went wrong and it drew more than 5 amps, it would trip this out, but it will cut off the power to all my loads, not just the thing that went faulty. So that could be a pain. It might be cheaper just to have one fuse or breaker, but if everything's wired together and one thing goes wrong, it cuts power to everything. So that might be very inconvenient. So it's better to use one fuse or breaker for each thing or each group of things that you're using. Also, if you wire things separately, you can choose the correct value fuse for each thing. So if you have a load of low power things, then you can fit a low value fuse and keep the high powered thing wired to a higher value fuse. That way, if the low power thing went wrong but didn't draw enough to trip the fuse of the high power thing, you could have issues with that. So that's why that is the way it is. So on this diagram here, I've only shown the positive wires, but obviously everything also has a ground wire. All the grounds are connected together. It just makes the diagram easier to see. So that's for the low voltage side of the system. So let me recap. We have solar panels coming in, goes through a meter, goes through a switch or breaker depending on what you have. A switch is the minimum that you need. Then we go to the input of the charge controller. The charge controller charges the batteries through this battery lead here, go through here to a switch and a breaker. So if a fault occurs in here, this trips out and disconnects this. Also acts as a switch, so I can turn it off if I want to work on other things. Then we have the main lead going down to the battery bank, which is down there, and there's a main switch here to disconnect the batteries if I want to work on the rest of the system, or if I have an issue and I quickly need to disconnect the batteries. So that's how that works. if I also want to explain something else, because we are using an MPPT charge controller, then the solar panels are wired in series to produce a higher voltage than that of the battery. We're working with a 12 volt battery. I have my solar panels wired up for 60 volts because I have 3 in series. The guy that I'm doing this for has 2 panels wired in series, so there'll be about 40 volts. So 40 volts at the solar panels for a 12 volt battery bank. So what happens here is the high voltage from the solar panels at a relatively low current, say 6 amps or 100 watt panel. So we have 40 volts at 6 amps goes into the charge controller, and the charge controller outputs say 13 to 15 volts out of the batteries, but at a far greater current, because the power going in equals the power coming out. Now, because we have a high voltage low current on the input, we have low voltage high current at the output, and that will explain why the wires between the battery terminal and the batteries is a lot thicker than between the solar charge controller and the solar panels. I will demonstrate this here. This is the wire from the solar panels. This is actually 20 amp wire, but it only needs to take 6 amps. And the wire going to the batteries has to take 30 amps in this case. The maximum output of the charge controller is 30 amps, so the wire going out to the batteries is a lot thicker because it can carry a higher current. That's the beauty of using MPPT charge controller, is that you can wire the solar panels in series for a high voltage, but only a low current flows in the wire. You can use thinner wire and place your solar panels a great distance away to get the best sun. So that's how that works. Now, that's the DC side of the system. I will point out here that I don't have a meter on the load side, and I do have a meter on the solar panel side, but I don't need to. The reason for that is that my solar charge controller has a remote meter. Remote meter connects to this terminal here, so that meter isn't necessary. What I have is a remote meter. This is the MT50 for the Tracer charge controller that I have, the Tracer BN. This meter also fits the Tracer A series that the gentleman that asked me to do the video has. He has what I believe is a Tracer A series, and you can plug in the MT50 meter, the same as one I have here. And if I focus, we have this side that gives you the solar panel readings. So that gives you the current and the voltage of the solar panels on the input. The middle set of values shows you how much current is going into the batteries or coming out of the batteries, depending whether you're charging them or discharging them. And this set of figures here represents the load output. So that would be the meter that you would have here. So I don't need these meters, separate meters, because this is all built into the MT50, which is one screen, shows me all this data, and it tells me all different things. It can tell me how much energy I put into my batteries today, in the last month, and ever since I set this up. We have the voltage of the battery and the charge or discharge current. It tells me the power coming out of the solar panels, volts, amps and watts, and it tells me the status of the charge controller, it tells me what my load output is. So this takes place of the load meter, gives you volts, amps and watts. If I turn something on, it might tell me. So that would be what load you're using. So all this information is in one display unit. Saves a lot of wiring and trying to fit in meters into your panel or whatever. So that's a possibility. But now I will focus on the AC part of the system, because the gentleman asked me how to wire up his inverter. So we start at the battery bank. We go through the main switch that I showed you down below. That's the red switch down here. Then we take a branch off this side to a switch. So this switch would turn your inverter on and off. And then you go to a fuse or breaker. Again, if you're using a breaker, the plus side of the breaker goes towards the plus terminal of the battery bank. From the fuse or breaker, we go to a inverter meter, as the gentleman wanted to know how much current his inverter was drawing. So again, the plus of the meter faces towards the battery bank, and the minus of the meter goes to the plus input of the inverter. I'll just take you down here. Now we have the main switch for the battery. Then we have a branch off that goes to I don't have a switch for the inverter, but I have a circuit breaker inside here. It's a 25 amp breaker, and then from the breaker I go to a meter. That's this meter here. This meter registers up to 60 amps, but I have a 300 watt 12 volt inverter, and the maximum draw of that is 30 amps. Now I said I have a 25 amp breaker. That's because I don't use the full output of the inverter. So at maximum the meter would read 25 amps. So from the minus of the meter we go to the positive, we go to the red terminal on the inverter, and then we have a ground connection for the inverter. The ground goes back to the ground of the battery bank, and I also have an earth wire that gives electrical grounding of the inverter for safety. And the earth wire is, can't see around here, but there's a green and yellow wire that goes to the earth outside. So that's for safety. This meter has a built-in shunt. Shunt is built into the meter. It's a lot more convenient to use a meter that has a shunt in it. Also, that when you choose your battery main switch, it needs to be able to take the maximum current drawn by your inverter. In this case it's 30 amps, but if you have a bigger inverter, there will be something to consider. This switch here is actually out of a jump pack for starting a car, so that's a fairly chunky size switch. So that's that. Also, all the wiring between the meter and the breaker and the inverter needs to be thick enough to carry the maximum load current of the inverter. So that's something to bear in mind. So this is Solar Tiger with an explanation of wiring up your system. I hope you found this helpful, and if you need to know anything else, please ask. I did see that the person who asked me to make this video had the eBox Wi-Fi. It plugs into the same socket as the remote meter, and you can read the values remotely, but it might be a hassle to get your computer out every time you want to take a reading. So I would say, to simplify some of your wiring, why not give the MT50 a try? It puts all the readings you want in one place, in one display unit, and it looks a lot neater, and you can mount this wherever it is convenient. It doesn't have to be in the same place as the charge controller. You can get a longer cable and you can place it a distance away. So that's the MT50. It works with all the Tracer charge controllers, and so this is the MT50. It allows you to turn the load on and off as well. There we go. I accidentally turned my load off. I turned the light on and wondered why nothing happened. So, right, so if I go to the load, so you can see now that to my load terminals, which is here, and on the meter that you would normally have here, the MT50 is showing that I am drawing 0.4 amps, which is 5.6 watts. So I'm running this light, and I have some USB chargers and other things that I have connected to the load output. So I can see what power is being drawn, and with one button I can simply turn them off again. That's very convenient. I don't have to go in the cupboard to turn things on and off. I can turn the load on from the meter. I'll push this button and I'll point you at the light, and I can turn it on or off. So that's another convenience thing. I can replace this switch. The MT50 can turn my loads on remotely. So that is Solar Tiger saying thank you for watching, and I know this video has gone past the half-an-hour mark, but I hope this is useful not only to the person who wanted me to explain this, but to other people. So this system is using an MPPT charge controller, so that's why the solar panels are wired in series. If you have a PWM charge controller, you wire your solar panels in parallel, and the current flowing into the charge controller is the same as the current flowing out, because it does not do any DC to DC conversion. Basically, when the batteries need a charge, the charge controller connects the solar panels directly to the battery. So that's the only difference with PWM. It also means you'll need a thicker wire between the solar panels and the charge controller, because the current is the same in the whole of the system. So this is Solar Tiger saying thank you for watching, and until next time I say goodbye, but if you need to know anything else, please ask. Thank you.